So arguably the most fundamental equation in all of mathematics, and thus one of the most important, is what's called a linear equation. And by definition, all a linear equation is one that can be written in a form like this. But that's not super useful because typically linear equations, when you see them, will look nothing like this, and maybe more like this. Maybe a little more informally, we can define them as equations, where your variable isn't squared or cubed or underneath a radical, or anything like that. Nor is it in the denominator, or inside some function, like sines or cosines or logs. Solving these linear equations is something you definitely want to be really good at, because what you'll see is our goal for a lot of more complicated equations is just to rewrite them so that they become linear equations. The assumption being that once they're linear equations, we're good in solving them. In this video, I'll show you what I think is the easiest way to solve linear equations, although there's lots of other options, and use this method on 3 different examples, encountering different issues and pitfalls as we go, and showing how to deal with them. Finally, I'll leave you with some practice questions that you can try on your own. Anyways, without further ado, I present to you the CCR method. Rather than speak abstractly, I think it'll make more sense to see this method in the context of a problem, so here's example 1. The idea with the first step is to concede that generally speaking, students hate fractions, and they hate anything that even resembles a fraction. So our goal in step 1 is simply to get rid of anything that looks like a fraction, to clear all the denominators. To accomplish this goal, you want to be able to see the different terms. In this equation, we have 4 different terms, but only the first term has a denominator. So to get rid of all the denominators, all we have to do is multiply each term by 2. Definitely take a second and make sure you can reconcile all the changes that got us from line 1 to line 2. It's not meant to be obvious, especially the first time you see it. But if all those changes do make sense, we can move on to step 2, where our goal is to combine like terms. The nice thing about linear equations is when we say like terms, there's really only 2 different types. The types that have the variable x and those that don't. I like to start with the terms that have an x in them and move them all to one side of the equation. Which side of the equation is totally up to you, but I like to choose the side of the equation that keeps them positive. So in this case, I'm going to move them all to the right. And just to be clear, when I say move the terms, what we're really doing is adding or subtracting to both sides of the equation to keep it in balance. So for the negative 6x term, to move that to the right, I'm going to add 6x to both sides of the equation. And for the positive 5x term, I'm going to subtract 5x from both sides of the equation, which has the effect of moving it to the right side of the equation. Now that we've combined all our terms with x's in them, the so-called linear terms, all we need to do is combine all of our terms without x's, the so-called constant terms. We want to move those to the other side of the equation, so the left side in this case. So to move the 10, we just subtract 10 from both sides of the equation. Again, before moving on, make sure you can see the changes that bring us from line 2 to line 3. That algebra could easily be shown in 3 different steps, although I'm just going to show it in one step, both for the sake of organization, and also I think it'll really help you to think of that as all one big step. Moving on to our third and final step, all we have to do is multiply by the reciprocal. And you might be like, nah, I learned this in a different class and it's way easier than that. All you gotta do is divide both sides by 3. Okay, really we're saying the same thing. You might argue I'm using unnecessary math jargon. However, I think thinking about it my way might be beneficial when we get into harder problems in future examples. One way or another, we want to isolate our variable x, which currently has a coefficient of 3, so we got to get rid of that 3. The way I think about it is 3 written as a fraction is 3 divided by 1, and you obtain the reciprocal of a fraction just by flipping it upside down, so the reciprocal of 3 is just 1/3. If I multiply both sides of the equation by 1/3, on the right side, I'll be left with just an x, and on the left side, my answer. A couple comments here. If you have a method that you really like and it differs from what you just saw, if you got the same answer, odds are your method's okay. Also, with linear equations, just like any other equation, if you feel the need, you can always check your answer by plugging it into the original equation. You should be able to change the x's into negative 3's in any of the rows above, but plugging it into the top row and making sure the left and right sides are equal is the only way to make sure nothing went wrong in any of the steps of the process. 4 minutes in and only one example down. Let's do a couple more examples, but maybe go through them a little bit quicker. In example 2, we again start out with 4 terms. However, nested inside the 4th term are 2 terms of their own. There's several ways you can deal with the parentheses that cause this phenomenon, but I think it's easiest just to get rid of them right off the bat and then start our CCR algorithm. We get rid of the parentheses by distributing, but be careful. Don't distribute a 3, make sure you distribute a negative 3. We have to make sure the negative hits each of the terms in the parentheses because we're supposed to be subtracting that entire 4th term. Now we move on to step 1 where we attempt to clear the denominators. Note this time there's 2 different terms with denominators, those values being 2 and 5 respectively. So to get rid of them, we multiply each of the now 5 terms by 10. The denominators are gone, which means step 1 is done, and we move on to step 2. We want to combine like terms. I like keeping the coefficient on the x's positive, so I'm going to add 30x to both sides of the equation to move the linear term to the left. And then note that we have negative 110 on the right side, which becomes negative 108 when we move the constants to the right side by adding 2 to both sides of the equation. Now we're ready for step 3, where we multiply both sides by the reciprocal of the coefficient on the linear term. Recall we first write 35 as a fraction, so 35 divided by 1. Then it's easy to see that its reciprocal is 1 over 35, which when multiplied to both sides of the equation leaves us with an answer of x equals negative 108 divided by 35. Because 108 is neither divisible by 5 nor 7, we can't reduce this answer, so we'll call example 2 good and move on to example 3. I tried to make example 3 as hard as possible. I threw in every trick I could think of, made the numbers somewhat miserable. What I'm getting at is if you can follow example 3, you're something of an expert on solving linear equations. First thing you might notice is much like example 2, we start out with some parentheses on the left side of the equation. So before we even get into the CCR method, it might make sense to just get rid of those guys. We'd get rid of the parentheses by distributing the 5. However, since we'd be distributing that 5 to rational expressions, things that kind of look like fractions, it might help to first rewrite that 5 as a fraction. We have 2 terms inside the parentheses, so we have to make sure the 5 hits each of the 2 terms. However, the first term itself contains 2 terms because the long division sign is implied parentheses. So we'll have to make sure that the 5 hits each of the 2 terms that make up the first of the 2 terms inside the parentheses. Wow! If you're still following, we can move on to step 1, where we'll try to clear the denominators. You might notice that there's 3 different denominators this time, a 4, a 6, and a 15. In example 2, when we had a 2 and a 5 in the denominators, we just multiplied the 2 of those together to get a 10, which the skeleton used to clear the denominators. You might think that here we should just multiply together the 4, the 6, and the 15, which would give you 360. And while that would work, it would make the numbers bigger than they need to be, which would make the arithmetic harder than it needs to be. Really what we'd like is the smallest number that is a multiple of 4, 6, and 15. And while there's several ways to come up with that answer, the one that I prefer is to consider their prime factorizations, informally the parts that make up each of these numbers. You create a 4 by multiplying together 2 2's, you create a 6 by multiplying together a 2 and a 3, and you create a 15 by multiplying together a 3 and a 5. What we want to do is create the smallest possible number that is a multiple of all 3 of these numbers. To be a multiple of 4, its prime factorization better contain 2 2's. To be a multiple of 6, its prime factorization better contain a 2 and a 3, but we already have a 2 in there, so all we got to do is add a 3. Similarly, to be a multiple of 15, its prime factorization better contain a 3 and a 5, but since we already have the 3, all we got to do is add a 5. The least common multiple of 4, 6, and 15 is just the product of 2 2's, a 3, and a 5. In other words, 60. We'll have the skeleton throw a 60 at each of our terms, which will suffice for getting rid of all the denominators. In the first term, 60 divided by 4 gives us 15, which we can verify by looking at the prime factorization of 60 and getting rid of the 2 2's that make up a 4. Similarly, in the second term, 60 divided by 6 is 10, and in the third term, 60 divided by 15 is 4. That gets rid of all the denominators, but before we start step 2, it's a good idea to get rid of all the parentheses. It just makes life easier, so we distribute as necessary. Now we're ready for step 2, which means we bring out your favorite cowboy to combine like terms. Don't act like you don't love the animation. To keep the coefficient on the linear terms positive, I'm going to move them to the left and then move the constant terms to the right. That concludes step 2, which only leaves step 3, where we multiply both sides of the equation by 1/87th, the reciprocal of 87, the coefficient on the linear term. That tells us that x equals 15 over 87, but 15 is divisible by 3, and 87 is also divisible by 3, because the sum of its digits, 8 plus 7, is 15, and 15 is divisible by 3. Anyways, the point is just that we can reduce our answer to 5/29. And that's the end of example 3. If you want a little bit more practice with linear equations, here's 3 examples you can solve on your own. They should have an increasing level of difficulty and be fairly similar to the 3 that we just worked out. Hope that helps.